Good morning. Get settled, because we're about to start. Okay. Okay, so good morning, first and foremost. Welcome to the new episode of Control Systems 1. In the previous classes, we have made a point that control systems is this discipline that likes to see the universe as a bunch of blocks that have inputs and outputs. We call these blocks systems, and we imagine a system as, if you want, the simplest thing you're able to understand. Okay, it's a mapping between an input and an output signal. And we said, look, systems, of course, can be, they come from the laws, the equations come from the laws of physics. There's plenty of different varieties of systems. And we gave a description on some properties of systems. So we classified them as linear, nonlinear, causal, non-causal. And we got to the point where we restricted the analysis of the systems that we care about to these linear time invariant systems. And we said, okay, but linear time invariant systems, they're nice, right? Why are they nice? Because they're easy in the sense that the mathematical description is straightforward. They have some very neat mathematical properties. Linearity, for example, the superimposition of effects is very useful. But we noticed that these systems really are not representative of what's actually going on, right? Because the things out there tend to be nonlinear. But we noticed at the same time in last class that if we proceed smartly about it, we can always use linear time invariant systems as approximations, local approximations of nonlinear systems. So if we linearize a nonlinear system around some special points, which we called equilibrium points, we get a good approximation of the dynamics of the nonlinear system. Now, what is a good approximation? Depends on the application. How far can we move from the equilibrium points up to which the linearized description of the nonlinear system is still good? Well, that depends on the application. Depends on how nonlinear the nonlinear system is. As we mentioned before, linear time invariant systems are a subset of everything that's going on. Nonlinear is everything else, so it's difficult to generalize about nonlinear systems. You always have to go and see what is it specifically that we're talking about. So we introduced these linear time invariant systems. We looked a little bit that these systems were best represented through the introduction of the special variables, which we call the state variables, which are variables that basically represent and encode the memory of the system. Summarize everything that happened since the beginning of time, since Adam and Eve, up to a time t0. And then, thanks to this introduction, only by knowing the state variable at time t0, plus whatever is the input signal between time t0 and a current time, present time t, it is possible to express the output. So this was interesting. We wrote down these state space representations of linear time invariant systems, which is the x dot equals ax plus bu equation coupled with the output equation y equals cx plus du. And we recalled that, of course, we've got a u at t as input, we've got our system, and we've got y of t, which is the output, right? So remember, U is the input, Y is the output. In this course, we just study single input, single output systems, which are CISO. And this means that the input is just one number, the output is just one number. But what goes on? So while the input is something that we get to choose, the designer, the controller gets to manipulate, the output, of course, depends on the system, right? if I poke a pendulum, I decide how to poke it, but the pendulum then just does what pendulums do, go back and forth, right? That's the output, whatever I can measure. So, but what's going on in the middle? What's the machinery, the mathematical machinery that links my input signal to the output signal? It's described by this equation here, and we can sort of represent it through this state variable, a set of state variables x. Because although u and y are single numbers, even in a cisosignal system, x belongs to Rn. Okay, x is a vector of n variables, where n is called the order of the system. So if xn is the order of the system, then we know y is a 1 by 1, so c must be an n by 1, d will be an n by 1, a will be an n by n, and b will be an n by 1. Okay? So once we introduced these state space representations of linear time invariant systems, which sometimes we can call the implicit representations, because, I mean, once you write it down like this, and of course, I forgot to write it, but you will have to include an initial condition, given this is, of course, a set of ordinary differential equations. We can call this the implicit representation because it implicitly already gives you the solution. Once you write that down and you know the parameters, the solution is just a matter of explicitating it. So in last class, we did a few calculations and we shown that we can explicit the solution in that way. So x of t we leveraged this concept of linearity, of superposition, and we said, okay, why don't we check if why don't we structure we search for a solution in such a way that it's the sum of two terms. The first one depends only on the initial conditions, not on the input, okay? So it doesn't matter, we called it the initial conditions response, or the free response. And so note that this does not depend on u of t. Plus another term, this one here, which we called the forced response, which depends only on the u of t and not on the initial conditions, okay? And this was nice. So once we figured out what the x of t was, we just used this second relationship here to figure out what the output is. Okay, cx plus du. Once x is known, we can plug x in here, and things are straightforward. And then we said, okay, now we know how to describe what is of interest to us. That is a really good chunk of systems in the universe, or at least we can describe them to some degree of good approximation. Then what's the whole point, right? Now we know how to describe them. They know how to behave given how we poke them and how we set the initial conditions. What are we going to do about them, right? So this whole course is called Control Systems. What does Control Systems want to do? The first thing Control Systems wants to do is stabilize a system. So what does it mean to have a stable system? So we introduced stability, and we said, well, we define stability in different ways. So always remember this, keep in mind that we've got the input, we've got the system, we've got the output, okay? In the middle here, there is these variables x that change in time. They're related to each other in some way, and they represent a network between what is the input signal and the output signal. No? Imagine it, I don't know, the input, you poke it here, then this changes this and a little bit this, and then this talks to this and whatever, and there are a million different relationships, and eventually something goes to the output. Now, it's just a pictorial representation to say that there is some relationship between different variables that is determined by the matrices, by the matrix A. And this link determines the relationships between input and output. So my point here is that one matter is how the input affects the evolution of these state variables. Another matter is how the state variables affect the output. So we study we define different kinds of stability, and we say, okay, the bottom line idea of stability is always the same. If you have to just remember it, is things don't blow up, okay? Now, the nuisances come in when you define things. What is these things? So it's either the states don't blow up or the output doesn't blow up given different circumstances. So there's Lyapunov stability, which says, hey, forget about the input. Let's put input to 0. If I set an initial condition to be something reasonable, something that is bounded, it's not infinite, and I let it go, then if the states, vary within a bounded region of some number that is finite, then we call that stable, right? Even if imagine a pendulum in a world without friction, right? You let it go, and it continues going back and forth forever. But it's bounded. It will never go all around. It will stay within the bounds given by the initial conditions. If instead you only thinking again, forget about the input, keep in mind the initial conditions, let it go, the system has a state evolution that converges eventually as time goes to infinity to a specific point, to 0, okay? Then that's a very good stability. It's a asymptotic stability, okay? And then we introduced this other concept that instead now it's more related to the things don't blow up, but things this time is the output, is no longer the state. And the idea is that of bounded input, bounded output. So if I send finite energy to a stable system, that is some measurement of the input signal, the norm of u is bounded, it's less than infinity, then the output is going to be bounded as well. Finite energy and finite energy out. Okay, that's a stable system. If these conditions are not satisfied, the system is called unstable. Now, last class, we had, although I said it right, there was a mistake in the slides. So asymptotic stability implies Bibo stability. If the states all converge to 0, well, the output is Cx, so it's just a linear combination of the states. It will be bounded as well. But the inverse is not necessarily true. So last time we wrote equal. Equal implies both directions. Actually, it's only one direction, right? Because you can have a bounded output, send finite energy in, get finite energy out, but some of the states could go nuts in the meantime. We'll get to that later on. So, very good. We now have outputs that we can describe of systems that we care about. We have a notion of what is the most important thing we care about, which is stability. How do we check it, right? How do we tell if the system actually is stable or not? And beautiful linear time invariant systems, we figured out that we can actually tell if a system is stable by just checking up what are the eigenvalues of the A matrix, okay? And we saw that, and we didn't really showed it in detail, but we said, look, matrices can be diagonalized. If we had a diagonal A matrix, this would be the answer, right? Today we're going to see how we can diagonalize matrices. But let's get to the conclusion before getting lost in how we get there. We saw that depending on what's the structure of the A matrix, so what kind of eigenvalues it has, if they are real and distinct, or complex conjugate, or repeated eigenvalues, so not distinct, we saw that the state evolution, therefore the output as well, could be expressed as a sum of particular terms. So in the case of all the eigenvalues of A being real and distinct, it was really nice because we got that the state could have been expressed as some summatory of E at the lambda IT times X naught. So the output, the evolution of the state and time included these terms that depended, exponential terms that depended directly on the eigenvalues of A. And it's nice if you think about it. It's like, wow, like A is not something that we get to choose. A depends on the system. It comes from the physics equations that one writes down. So stability is an inherent property of the system. And so we said, look, well, if we look at this expression, and we said that stability means if I give a bounded initial condition, well, this whole thing, I mean, Lyapunov stability, this whole thing, x of t has to stay bounded, must not go to infinity. Then we can see that, well, it really depends on the lambda i's up there, right? If those are positive numbers, well, if you have E at the 1t, you'll get something that goes up like this, right? So this would clearly not be a bounded state. As time goes, it goes to infinity. So if lambda I were to be equal to 0, well, you get E at the 0t, which is a fancy way of saying 1, and this stays constant forever, which would be not asymptotic, but still stable. It's bounded out. But if instead you have your lambdas that are all negative numbers, you would get a converging behavior, which is asymptotic stability, which is typically the most desirable outcome. We then saw, well, okay, but if the A matrix has a different structure, well, then we can express the outputs as, let's say, the lambda i's are complex conjugate. Fundamentally, the same truths apply. That is, you always have an output that is given by an exponential term that represents the envelope of some oscillations, okay? And this exponential term, the sigma, is the real part of the eigenvalue. So basically, everything we said before applies. So you would have asymptotically convergent behavior in case of sigma being less than 0, constant in case of sigma being equal to 0, and something growing if sigma is bigger than 0. On top of it, you would have some oscillations. So in case of sigma being less than 0, you would have some decaying oscillations. In case of sigma being bigger than 0, you would have some oscillations that eventually blow up. And in case of sigma equal to 0, you would have this thing going back and forth. This reminds you of the pendulum, right? In fact, you could see that if you go and check the example we did last time and then calculate the eigenvalues of the linearized A matrix in the case of the pendulum, you'll see that they are complex conjugate eigenvalues with the real part that is equal to 0. So what if instead we have repeated eigenvalues? Well, if you have repeated eigenvalues, you have to be careful, because with repeated eigenvalues, if you have repeated eigenvalues in 0, then you've got a polynomial output that eventually explodes. So what's the conclusion? And the conclusion here is really important, is that if you want to check the stability of the system, calculate the eigenvalues of the A matrix. If the real part of these eigenvalues is less than equal than 0, then you're game. The system is stable. All of them must be less than 0, the real parts. If at least one is equal to 0, then you don't have asymptotic stability, but you still have stability. If only one has a real part that is bigger than 0, well, the system is unstable. So today, what we're going to do is we're going to continue in the analysis of the properties of these time responses, and we're going to say, look, first, let's see how we diagonalize systems and what comes out of it. What can we infer from the diagonalized form? But before doing that, we will take a step sideways. Okay, before continuing in our analysis, we'll say, if you remember, literally from, I think it was like slide number 7 I showed you in the first lecture, we said, what is a signal? A signal is a mapping between two sets of numbers, right? And imagine the set from where you pick the numbers, like the time, let's say, set. If it's continuous, well, then you have continuous time descriptions, and that's what we've been talking about up to now, which is how nature works. But it's even possible that this first set from where you take the numbers that you plug in the signals is not continuous, it's discrete. Okay, imagine like the set of natural numbers, 1, 2, 3, 4, there's no 1.1, there's nothing in the middle, okay? Well, that kind of changes stuff, right? Because now, how does that change the way we write the systems, linear time invariant systems, how they respond? How can we evaluate stability from them? So why is it important? Today we're going to look quickly at how we can describe these discrete time systems. And they're important because computers use discrete time representations. So every time you will want to solve a differential equation on a computer, you want to implement a controller on a controller, as in one of the control logics that we're going to study throughout this course on a microcontroller, which is a simple computer, you will need to think like a computer does. You'll need to think in discrete time. So while pretty much everything that we say in continuous time is still valid for discrete time, details change. And it's important to keep these details in mind, at least know about their existence, so that once you are there, you can actually go and check things appropriately. So what's the biggest difference between continuous and discrete time? In continuous time, you've got your signals that are defined at every point in time. It's a it's a dense set, right? In discrete time, there's nothing in between. Oops. In discrete time, there is nothing in the middle of sampling instance, okay? So the signal is evaluated, sampled, at specific time instance. The specific time instance are called sampling instance. And what we are going to look at is discrete time systems where the sampling is uniform, the sampling period is uniform. It means all these sampling instances are equally spaced apart in time, okay? So we've got a constant sampling, it's called sampling period, TS, and then our world, from the point of view of discrete time systems, is just the states and outputs evaluated at those specific time instance KTS, where K is a natural number. So, at the end of the class, these are things that we'll have to cover. So, why is this relevant? Well, it's relevant, as we said before, because that's how computers do stuff. And computers don't have a concept of continuity. So if they don't have a concept of continuity, they don't have a concept of limits. If they don't have a concept of limits, they can't take derivatives. If they can't take derivatives, they can't solve differential equations. So we need to adapt a little bit to all of this. So how do things actually work? Because yes, sure, computers are relevant. That's where we implement our controllers. But still, we do it in order to interact with the physical world, and the physical world is continuous. It's not like we discretize even if you were running a simulation, you would be discretizing even the physical world. But the idea is that this discretization, this implementation on a microcontroller must happen in the middle of a continuous world. This is the plant we want to control. It's continuous. This is the reference signal, the error. These are all continuous things. Now, how do we transition between this world of continuity and this world of discrete time? Typically, there are two important steps. One is called analog to digital conversion. So a discrete time signal is typically called a digital signal. So we can, there's this first step that is an analog to digital conversion, or known that operates the sampling. So imagine E of t to be a continuous time signal, okay? Then after this sampling block, what happens is that we no longer have an E of t, but we have an E of k, where k is these sampling instance that we defined before. And we will get like point here, point here, point here, point here, whatever it is, okay? Then everything will happen in discrete time up to some point, and this everything is whatever we choose to, whatever manipulation we choose to do with discrete time data, for example, the implementation of a controller. And then in order to get back to the continuous world, there is an operation that's called digital to analog conversion, which can be done in many different ways, but the way we will focus on is the so-called sample and hold. So we have let's say U of k is the signal coming in discrete time, so it's just a collection of points. In order to transform it into a continuous signal through the sample and hold, which is a first order, let's say, conversion, all we do is we say we take at the specific sampling period, whatever the value is, and we keep it, the sample, and we hold it, we keep it constant up to the next sampling point. Imagine being a computer. You're giving a piece of data at now, okay? This thing is equal to 1. Then the next piece of data is not going to come in up to 10 seconds from now. What are you going to do in the meantime? You're going to assume that that thing stayed constant at the first value that was given to you. And you will change your mind every time a new value is communicated to you fundamentally. So this is the idea behind the sample and hold. You take the latest value, you hold it, 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 and so on. So from a continuous time signal, we sample it, and then eventually you can do this holding operation, and you will get as output this kind of step signal that is a reconversion of a digital signal into a continuous one. So keeping these things in mind, what we really want to understand now is, well, but say we know everything now about our continuous time representation of state space variables. How do we get to the discrete time one? Okay, so this is the final solution, and we're going to see a little bit how to get there. So the idea is that it is possible, of course, to transform a continuous time signal into a discrete one. But, and we can represent it in fundamentally the same way if we keep in mind what the nuisances are. But we have to be careful because the matrices that link the various actors in this game are different. So how do we get from one to the other? Keep in mind what a continuous time signal is. Say this is x of t. And when we actually showed at the blackboard how to derive this explicit representation, this x of t is equal to blah, blah, blah. We made the assumption that the initial time from where we were starting this calculation was t naught equals to 0, okay? Of course, we could have left it general. We just said, let's make it to 0 for simplicity of calculation. But if we had kept it just a parameter, said, okay, well, let's call the initial time t0, and x of t0 is the initial condition x0, then it would have looked like this, okay? I will keep this expression, deriving this as an exercise for you. Just go back to whatever passages we did last time, and suppose that there is an x of t0 instead of being equal to 0, and you'll see that everything is the same, but just you have to, if you think about it, the concept is exactly the same. All we need is a knowledge of the state at this point in time before the present, t naught, and the knowledge of the input between then and now. The knowledge of the input is indicated by the integral of this u signal between t naught and t, and all you need is the state variable that is the memory of the system evaluated at that particular time instant, t naught. So this is how things look. And if we now evaluate, so where do we want to go? Where are we heading to? This equation tells us how a continuous time signal works, right? But really, we want to know what's the dynamics of a discrete time system. So how are, for example, these values connected to each other? Say this is x, this is time instant kts. So this is x of kts. Say that this other time instant here, say this is the sampling period. So this point here will be k plus 1 ts, right? It's going to be kts, whatever it was before, plus another ts, plus another sampling instant. You would get xk of ts plus ts. So the question really here now is, how do we express the dynamics of a discrete time system? Basically, what is x of kts plus ts equal to as a function of whatever it was before? Okay, and possibly the input in some sense. It's basically the same thing we've done for continuous time, but expressed for discrete time. And the way we reach these expression is by using the continuous time representation and literally plugging in these two values that I just showed. That is, suppose that the time, the initial time at which we're calculating this thing, t naught, is equal to kts. So we start from here, okay? And then suppose that we're interested in knowing what is x at the next sampling instant, which is here. So if this is t naught and this is t, let's just plug in the equations. T naught equals kts, t equals k plus 1 ts, and we will get the relationship we need. So if we do these passages, you'll see that we get t, and we plug it in here, and we get x of k plus 1 ts. And e at the a, t minus t naught, well, t minus t naught is equal to k plus 1 ts minus kts, which is equal to ts. So we've got e at the ts here, that comes from this. And the rest is just plugging in, and here's just a substitution. Let's focus a second on this integral here that looks relatively messy. One thing to keep in mind is that we made an assumption, right? We said Well, the way the computer works, or at least the way we're describing it now, is that the input signal between two consecutive time instants is kept constant. We have the sample and hold approach. So this is what is expressed here. So how does this help us in dealing with this second ugly integral on the right? It helps us because if u of ks is a constant, we can bring it out of the integral, right? It's no longer a variable in time, so it's a number, and it's a number between two consecutive sampling instants, so we take it out of the integral. And at this point, the only thing that is left to do is to express this in a more decent way. So if you just make this coordinate transformation, you will see that this is the outcome. So basically, what we have to do is, why are we choosing this? We're choosing this because this argument here is really ugly. So let's try to substitute that with a single variable. We call it lambda. The lambda is gonna therefore be equal to minus d tau, and everything else is constant, so you don't differentiate it. And then if we evaluate, so here, of course, this integral is expressed in tau, which means these extremes are tau equal. Now we have to re-express them as lambda equal, because we did a change of coordinates. So we just plug in tau equal, let's call this tau A and this tau B. We plug in first tau A, then we plug in tau B, and we get these two extremes here. So all we're doing here is a trivial change of coordinates. There's no magic, no passages that are, no other assumptions involved. And we finally immediately get to the form we were looking, which is a relationship between what's the state at the next time step as a function of the state as the previous time step. That is, what is x? So notice how ugly all of this is. Like we have to write the continuous variable x evaluated at k plus 1 plus ts, okay? It's really a cumbersome notation, and so it is an assumption, it's a common practice to not show the ts. The ts is considered implicit, like you, yes sir? Whoa, wait a sec. Yeah, sorry, works like this. Can I throw it to someone there? And yeah, just pass it over.
Where did the minus go from the minus d tau?
Where did the minus go? From minus eta. Where are the etas here?
Sorry?
So where is eta? We've got a
no,
tau.
d tau. You wrote d lambda.
Yes, d tau. Where did the minus go? Good question. So when you actually do this change of the extremes, let's do it actually. If we plug in tau equals kts, we get k plus 1 ts minus kts, which is equal to ts, right? So this here, expressed in lambda, is ts. If we do the same thing above, expressed in lambda, this is 0. So basically, the inverse, the extremes of the integral have flipped over, and if we reflip them over, that's an extra minus that compensates with the minus of the d lambda. Okay? So what was I saying? Yeah, so the idea is it's really ugly to bring over this ts all the time because it's kind of obvious. This whole context is we're assuming a constant sampling time ts. So what we write is just x of k plus 1 is equal to something with x of k and u of k, where u of k, x of k means evaluated at the kts time instant. You'll sometimes find it written like this, sometimes you'll find it written with square brackets, sometimes you'll find it written as a pedix, like this. I'll jump between the different notations, it doesn't really matter, they're all equivalent, okay? So here we go. What's the point? This is the summary slide. We can go from continuous time representation to discrete time representation, assuming a uniform sampling instant period Ts and the sample and the sample and hold, which means keeping u constant between two consecutive sampling instants. we get then these expressions where the AD, BD, CD, and DD, which are the discrete time equivalents of the A, B, C, and D, are related to A, B, C, and D through these equations here. Note that C and D are completely the same, but this becomes AD and this becomes BD. So of course, these are a function of the sampling period. It's kind of obvious. It's intuitive that the sampling period represents sampling a signal, means throwing away data, right? I mean, if you have a continuous time signal, you have a lot of data picked to any points in time, and there's infinite data in the middle, right? If you discretize a signal, now you just selected a collection of points, therefore it's intuitive that you have less data. An interesting question would be, I have less data, but do I have the same amount of information? And that's kind of something we will not talk about in this course. You'll see it in, say, when you study signals. But there is a fundamental result there called the sampling theorem that tells you, hey, if you're sampling a signal, you need to sample it fast enough in order not to lose information. And what does it mean to lose information? It means now pretend for a second that you're just given a sequence of discrete time data points. Only from those can you reconstruct what the original signal before sampling was. Well, if you can't do it, you have not lost information. If you can't do it, then you lost information. So in order to be able to do this, there is a very famous result. We'll not get into it, but the idea is when you sample, you want to choose a sampling period that is fast enough depending what you're sampling. It's intuitive. Something is changing very quickly, you want to sample it very quickly, otherwise you'll lose information. Something is going very slowly, the seasons, like how much rain does it fall every year? Well, you maybe sample it once a week, it's okay. Okay, then, so this is important. This is a way to pass from a continuous time representation to a discrete one. Note that I've been talking about the implicit representation. This is how you write your x dot equals ax plus bu, right? Now, of course, the natural question, following the same pattern as we did for continuous time systems, is, okay, but how does x of k plus 1, how does x of k now look like? In the sense, what's the solution to these finite difference equations? We can find it by applying a trick. So this was the way we did it in continuous time. This was the way we did the solution in continuous time, right? Actually, this should not be a parenthesis. It's confusing otherwise. And okay, now we know that x of k plus 1 is equal to ax plus b, ax of k plus bu of k. Forget about the y for a second, because the y is easy. You just then do cx plus du. What's x at time 1? Well, x at time 1 is, notice, here we've got k plus 1. So on the other side of the equation, you want to put whatever you put on the left, 1 minus 1, right? Because it's k, which is 1 before k plus 1. So this is a times x of 0 plus b u of 0. Do you all agree with this? Yes, no, maybe? Cheer up, come on, fun stuff. Does anybody disagree with this, at least? No, good, thank you. So, what is x of 2 then? Remember, here we're just jumping between a data point and the next one, right? There's nothing in the middle. Like this representation doesn't conceive being an x 1 plus 1, 1.1, okay? There simply doesn't exist. There's a 1, a 2, a 3, a k. So what's x of 2? X of 2 is, let's just reapply the definition, x of 1 plus b of 1. But now we know that x of 1 is equal to this, so we can plug it in here, right? And what you get is, of course, okay, now you see, this I will get confused sometimes, because really if you look in the textbooks when they give you the discrete time representation, nobody is going to be nice enough to you to remind you that you have to calculate the discrete time version of it, okay? If you find an a in xk plus 1 equals ax plus bu, they automatically assume that that's the discretized version of the a, if you have a continuous time system introduced before. The bottom line is that these should be all ADs, but sometimes people will just forget and they'll write A and B, but keep in mind that this is now the discretized version, okay? It's no longer the continuous time it's not the same A as here. Okay, so remember, AD is equal to E at the ATS, okay, TS. So we can plug in x of 1 in here, and what do we get? We get AD times x of 1, which is AD x of 0 plus BD u of 0, plus BD u of 1. So what do we get here? We can rewrite it as exactly as this, right? A square, AD square plus these terms here. Now what if we do it for x of 3? Well, if we do it for x of 3, it's the same thing as above. It's AD times x of 2 plus BD x of 2. U of 2, sorry. So what does this mean? It means we'll get a cube dx of 0 plus what? Plus AD square BD u of 0 plus AD plus AD BD u of 1 plus BD u of 2. What if we continue going? If we continue going, you will notice a pattern, okay? And the pattern is that we can write the explicit representation in a very similar way as we did before, with some state transition function between the initial conditions and the, actually here we should have put the initial conditions and the system, and another term that represents the forced response, that is the contribution of the input signal to the output. And how do we get these functions here? Well, just it's by inspection. Now, if you do this game, you see that x of k is always equal to, see here we had x of 3, here we have AD at the 3. So it's going to be AD at the k times x naught plus something. Something, of course, is going to be a sum. Notice how you've got all these terms that are aligned here in a very interesting way. And what is the idea? Let's make the sum go from 0 to some value, up to what value? So it's always, if this is k, here it's always k minus 1, no? Because xk plus 1 on the left side has a uk at most on the other side. So here you're definitely going to have a u of I. And how is it related to these matrices here? Well, if you put some patience into it, you will see that there's definitely an A and B game going on here, AD and BD, where A has an exponent that is k minus 1 minus I. So the idea being that at the most current time instant, you will have the AD going to 0. Basically here, this is an identity matrix. It goes away, so if you write it like this, it turns out to be correct. So this is the discrete time representation of the evolution of a discrete time system. It's fundamentally the same as before. We always got a free evolution that depends only on the initial condition. And we've got a forced term that depends instead only on the input. And what is the biggest difference that really has profound implications on what the next step is? Is it time for the break? We've got 2 minutes, right? No? 1? I better be quick then. So we've got this state transition matrix that passed from being an exponential term, E at the AT, to being just, so whatever, you just lost the opportunity to have this, to be the power of a matrix directly. And since before we said, hey, but stability was related to the eigenvalues of A because we had this exponential term. Now we don't have the exponential term anymore. There must be something going on, right? And in fact, this is exactly the case. Now, if we were just to suppose that AD is a diagonal matrix, and we'll see just in a few slides how this is a good assumption, then the xk would be represented no longer with like in the continuous time, it was E at the lambda I t x naught, but with this lambda ik. So we'll continue after the break. So good.
Can you go back? Yeah. Here, exactly. This point we wrote here looks pretty much similar to what we did in last street. Looks pretty much like that. We're going to use something similar. Because when you have something in that line, we are also on the initial condition, and that banks up these tones. Because there, it's S to the power of 6, and here it's A to the power of 6.
It's weird that you're making this connection. So I think that the reason for which you're making this connection is wrong. So no, there is not a connection in what you're talking about. But the intuition is right, because yes, absolutely you're going towards that. But I don't see it coming out from here. It's nice that we have 50%. So the idea here being that, first of all, the class stuff that you studied works in continuous time. The big deal here is that there is nothing defined between two consecutive dimensions. It doesn't exist. The representation doesn't exist. In the world of natural numbers, there's no rational number, right? But it's finished. So you cannot do Laplace transformations in discrete time. But there is an equivalent transformation. There is an equivalent transformation. It's called the T transform. And we will hint to it here. We will do it later on. We talk about Laplace transformations, which is going to be the rest of the course is only about Laplace. Laplace is the secret of control. That's what makes everything deal with. So we're definitely going in that direction. When you do Laplace to discrete time, you have to be super careful and introduce a new transformation, which is called the T transform. You will not go on like this. I
guess I'll wait for the lecture.
This is concept introduction back. Getting it right? Because the concept of separation is begun. Yes, two times. This introduces back. This is yes. That's
There is a time delay, if that's what meant, lag when you transform the system to discrete time. Now, I don't want to get too much into detail here, because we could make a course on the discrete time systems, and there are courses like on discrete time systems. What my objective here is for you to understand that if you are running a differential equation on a computer, which you will do every time you implement something, don't check stability with what I do. You have to check stability in a different way, which is the next slide. Okay? Because you have to just, to answer your question, it depends how you discretize it. We said just sampling. That's a simplistic approach to it. There are many different discretization approaches you can use. You can choose to, because the whole question is, the whole deal boils down to a differential equation. A differential equation x dot equals whatever you want is an x dot. It's the dx of t in dt. Right? It's a derivative. That's the derivative. What's a derivative? What's the definition of a derivative?
change of phase in time.
No. I'm asking you the mathematical definition. It's the limit for h that goes to 0 of the incremental gain. Which is x of t plus h minus x of t over h.
Nee, contactvergelijking. Wil je het eens vertellen? Nächste Woche, Dienstag, Mittwoch. Ich möchte eigentlich etwas dazu sagen, aber ich kann mir nicht dazu fragen.
What you're doing is you take this, you bring it to 0, as these two points press close to each other, eventually fall up on the same point. In fact, somebody told you that the derivative is like the local tangent, right? Limit goes h that goes to 0. This is critical. Like, I could ask you, what's the definition of a limit? Let's always play the y game. Math is fantastic. Definition of a limit. If you go back to whenever you study limits for the first time, I find it magical. It's fantastic. It's the first time since you study math at the beginning of your elementary school to tell you about the numbers, is that you introduce a concept, an operation that's purely positive. You don't just do it by calculation. You have to introduce like the limit. The limit operation is take an epsilon bigger than 0 as small as you want. How small? Well, the smaller, the better you understood the concept. Okay, so you kind of it's not well determined. It's not like 0.0000. But a computer can't do that. A computer, you must tell epsilon is equal to 0 going 10 minus 12, 10 minus 15, whatever it is, okay? And there are issues there then, how much memory the computer has, but the bottom line is that a computer cannot do this, okay? So a computer cannot do derivatives. A computer can do finite differences. This h, epsilon, is going to be bigger than 0, but some specific number, whatever it is, okay? At that point, you have a finite difference. So you can only consider a slope that jumps a little bit. And at that point, you can ask yourself, well, you want to do it like this? You want to take the backwards one? You want to take 4 numbers and just do an average? You can do whatever you want, right? It's a whole field called numerics, which is the thing I'm focusing on. And at that point, you have different flags, but intuitively, yes, you have flags. And how you distribute them. Let's say, worst case scenario, you've got a one-time step in there.
I wanted to ask, you talked about asymptoticity, but where in my real physical system, something like that?
Take a pendulum, okay?
I mean, real is still not infinitely long, because we're looking at...
Okay, good point. Yeah, okay, sure. Tell me in physics one thing that is infinite.
Nothing.
So you can't apply a matrix of judgment of physics to mathematical description, right? Mathematics tells you what is the behavior. Then of course, you know, they tell me, I've never been there, that there's a door in Japan, very fancy, you get to give it the next minute. There's a door in Japan that is beautiful, it has all these statues like carved into it, it's perfect, like you can see how much work went into it, it's like, it's huge, I think, but just at the height of human eyes, one of these statues is flipped over, like completely rough, it's upside down. People are like, why in the world is it like this? And they say that it's done on purpose because humans should never be perfect, because otherwise the gods would be upset, right? They would be jealous. It's kind of the same things between math and physics. Like math is the perfect representation. Physics is never as perfect, but because it's a real thing. It's like, but of course, this is not a technical approach to the problem. The bottom line is that infinite, any adjective in physics makes sense only and exclusively if it's referred to something else. So infinite means very long with respect to. Okay? So infinite time here has some stability means it's a long time with respect to the period of the Remember, every time you talk in physics, if you put an adjective big, small, half, full, fast, slow, it's always wrong. Like big red cross minus points unless you quantify or you specify with respect to something else. Because absolute adjectives make no absolute sense. Yeah.
Hi, I'm the one who wrote you yesterday.
Yes.
Okay, sorry. Is it okay if I just talk in the first?
Yeah, you can set this up in 7 minutes.
Oh,
please take only a minute because I have a lot of stuff to go through. And I'm
yeah,
not
sure,
I
will say we have a CV check.
Do whatever you want. Of course, don't
there's
do whatever you
stuff
want
to take.
because otherwise I'll have to
Thank you.
call in the police. But, question. The reason for which I introduced the message
Yeah, he doesn't really understand that. He might look at yes, please.
Hallo zusammen. Darf ich schnell um eure Aufmerksamkeit bitten? Okay, sure. I should talk in English. So I'm here from the AMIF Contact, the company fair. Many of you already saw the booklets and the pens. Feel free to take some along. It's a good possibility to see what we can do after we finished our studies. And we have the possibility to make your CV check and new CV pictures. It will be done by professionals. Feel free to come and have a look. It's on Tuesday and Wednesday next week. And today is a small apero with a talk about what is consulting. Just subscribe on the AMIF website if you want to come along. Thanks.
Okay, so where were we? Settle down. Okay, so where were we at? We said we understood the discrete time systems are approximations of continuous time ones. We just evaluate things at specific points in time. There's something in the middle. Therefore, the evolution between two subsequent consecutive points in time is regulated by difference equations, finite difference equations. These ones here. And we get to pass from one representation to the other through some fancy formulas that depend on the period, the sampling period. Lower your voice. So, as stability, which we understood is something very important to control systems, was described in continuous time through the eigenvalues of the A matrix, it is legitimate to ask ourselves, well, what happens if the A matrix now has been discretized first, and the conclusions we took from continuous times came from the fact that the explicit time response in continuous time had this matrix exponential term, E at the AT, from where we said, well, look at the lambdas, they have to have a negative real part so that the exponential is convergent and whatnot. Now, we see that this, the equivalent representation is no longer an exponential term, but it has this matrix power. So you'll just take my word on the fact that if we could diagonalize the D matrix, and we can, if the eigenvalues, for example, are of the A matrix, of this AD matrix, are real and distinct, we can represent the solution with a completely equivalent way as the similar way as the continuous time, where the E at the lambda IT now is replaced by this lambda I to the K. So the conclusions for stability for discrete time systems are no longer that your lambda I needs to have a real part that is negative for asymptotic stability, equal to 0 for stability, but now it's about the magnitude of the eigenvalue. Because, why? Because, well, here you have one, so you have lambda at the K, it's a power, right? So if lambda is equal to 1, you will have this 1 at the K, as K now is time, right? So as time proceeds, K goes to infinity, 1 at the infinity is always 1, it means that your response will be bounded, okay? If instead lambda is a number that is smaller than 1, what you will get is that as time goes by, k1, 2, 3, k, your dynamics is going to be dominated by this term that is, let's pretend, 0.5 at the k. It's something that as you multiply it by itself, it becomes a smaller number, right? So it's going to be something like this. Asymptotic stability now is described by having the magnitude of your eigenvalues being within the unit circle, having magnitude smaller than 1. If instead any of your eigenvalues, lambda I, has a magnitude bigger than 1, what's going to happen is that you have a bigger than 1 number, let's say 2, at the k, this becomes 4, 8, so on, and explodes, right? So you've got a system that is divergent. It's the output or the state, the evolution is going to be unbounded, hence it's unstable. If instead you have all your eigenvalues that are within the unit circle, but at least one is on the unit circle, well, you have a component of that output that it's constant, basically, so you still get stability. But so this would be this case here. You still get stability, but not asymptotic one. Now, here it's not represented in this slide, but really another interesting behavior, somebody could say, okay, wow, but where are the oscillations? Where's the up and down part? Well, it turns out that as we say that the stability is regulated by the magnitude of this eigenvalue, but we haven't talked about the sign, right? It's stable even if it's minus 0.5. It's just that if you have the minus, then every time instant you're switching sign because the power of an even power of a negative number is a positive number and so on. So if you had the lambda equal to minus 1/2, for example, which would still give you asymptotic stability, but it would bounce up and down like this, okay? So you would get the equivalent of your oscillations before. So what if instead we had, so this was this kind of answer is this kind of formulation of the state evolution is for real and distinct eigenvalues. Now what if you have complex conjugate eigenvalues? Same story as before. I spare you all the passages, but the idea is if you have one part that represents is related to the magnitude of the eigenvalues of A, and it's given by, so that the eigenvalue be a complex conjugate number, so they have a real part, sigma, and an imaginary part, omega. So this basically rho is, so if this is the imaginary plane, this is the real axis, you've got your sigma here, your omega here. This would be your rho. It's the magnitude of your eigenvalue. If this is smaller than 1, we got asymptotic stability. If it's equal to 1, you've got stability. If it's bigger than 1, at least one of the eigenvalues, you've got instability. So the conclusion is the same as the other one, plus an extra little complication of phases going around. Let's not get into that now. My point being that if you want to check for stability of a discrete time system, next time you're going to implement your first controller on a computer, please don't look at the sign of the real part of stuff. Go and look at the magnitude of the eigenvalues, because if you're discretizing a system, then the considerations on stability change. Does this make any sense? I must say that your feedback is not very informative. Like whatever I say, you just look at me and stare. Give me all your money. Okay. Anyway, so that's it. So this was our little excursus on discrete time systems. It's the end of the side step I was talking about before. Now we got to the point where we can tell how to express the implicitly and explicitly both a continuous time and a discrete time system, and how to tell a basic analysis of the stability. In both cases, it depends on some structural properties, on the eigenvalues of the A matrix, whatever A is in the specific case. Now let's go back a second to continuous time signals and move on. So up to now, we said, look, if we had these diagonal matrices, we could write the answer in a neat way, and we took a bunch of conclusions from there. And at some point, we even said, when we introduced the state variables, we said there's many different choices of state variables you can make, right? State variables are something that contain memory, that contain energy, or we said something wishy-washy like this. But really, there's infinite representations that one could have of a system. And it's very easily seen through similarity transformations. So say that you've got your linear time invariant system, x dot equals ax plus bu, right? And say that you've got another set of state variables, let's call them x tilde, that are related to the x state variables that we chose through a coordinate transformation t. Keep in mind, this is an m by 1 vector, this is an m by 1 vector, t must be an m by n matrix, square matrix, okay? Now, it's actually a coordinate transformation if it admits an inverse, so we can say that this is true as well. So, T matrices that satisfy these equations, you can come up with very many, have the following effect on the system. Say you've got your linear time invariant system, and now you want a change of coordinates. You want to re-express things, just look at things in a different perspective. That's what a change of coordinates is, right? So what we're doing is we're just substituting x with x tilde. So let's go and see. Here, x is equal to t x tilde, right? So from here, we can say that x dot is equal to t times x tilde dot, right? Because t is not a time-varying term. So we got this part here, and here instead all we're doing is just substituting. At this point, we don't like the t on the other side, so we left to multiply both sides of the equation by t inverse. And what we get is that these two guys go away, and we have t inverse at, t inverse b, ct, and d, which we can call new A, B, C, D matrices. No, sorry, this is the same. And basically nothing has changed. You get the same exact representation as before. X dot equals ax plus bu, y equals cx plus du. I mean, in first place, if I had told you that x was not an x but was a z, you would have, believed me anyways, right? It doesn't really matter what we write there as an x. There's always a linear time invariant system is. So what does this tell us? It tells us that if we have a linear time invariant system and we do a coordinate transformation in that way, we get another linear time invariant system. And the cool part is that these two representations actually have the same identical time response. So now what if we choose this T matrix to be something particular? For example, a collection of the eigenvectors of the A matrix. So remember that once you have, why are we going in this direction? Because we saw that the fundamental properties of the system, such as stability, depend on some structural values of the A matrix, which are the eigenvalues. And the eigenvalues and eigenvectors are defined to satisfy this relationship. Now, basically, if we crank a vector through the A transformation, you can always imagine A is a matrix, but the geometrical interpretation is a linear transformation, no? So you send a bunch of vectors in, a bunch of, components in each direction of the defined by the A space. What A is doing is it's taking each one of your input coordinates, rotating and scaling them, right? And then you get as an output something, typically another vector. In the particular case of eigenvalues and eigenvectors, what you get is lambda IB. So why are these eigenvectors so special? They're special because they're like the favorite directions of the A matrix. Now, they're those directions that if you send something in as input, there's no rotation involved. The output is always those directions, just multiplied by a number. And those numbers are called eigenvalues, okay? So it's kind of like the favorite point of view of the A matrix, if you want. So if we, of course, please remember that A here is the A of x dot equals ax plus bu. Therefore, A is an n by n matrix where n is the order of the system, that is the dimension of x. If we just write the B matrix to be a collection of all the eigenvalues of the eigenvectors of A, so B is an eigenvector, so B, if this is an m by n, this is a 1 by 1, this is an m by 1. Okay, it's a vector. So a bunch of n by 1s, n by 1s put in column 1 next to each other will make an n by n matrix. Then it turns out that by definition, A times V is equal to V times lambda, where lambda, this is just the vectorial representation of the definition of eigenvalues and eigenvectors, where lambda is a diagonal matrix that has on the main diagonal the eigenvalues of the system. So this is how we diagonalize the A matrices. So this leads us to a very important concept, which is that of modal decomposition. Basically, if we express, so we understood that x dot equals ax plus bu represents a description of what we're studying. We know that x's can be pretty much, there are many different x combinations we can choose to represent appropriately the same problem. We can actually jump between the different x representations, different coordinates, by some transformations functions, some T matrices that represent coordinate transformations. If we choose a special coordinate transformation that is linked deeply to the structural properties of the matrix of the problem we're solving, that is, to the eigenvectors of the A matrix, the system now gets represented in the simplest possible way. That is, since we have x tilde dot equals to A tilde x tilde plus whatever, now let's just pretend u equal to 0, we know that x tilde of t is going to be equal to E at the A tilde t times x tilde x naught. This is exactly the same thing that we studied last class and at the beginning of this class. It's the explicit output of the state space representation, but just after the change of coordinate. Before we called it x, now we called it x tilde because we know they have the same dynamics. So, well, but now if we choose t equals to b, that is the modal decomposition, now A tilde is actually a diagonal matrix. This is E at the lambda t, x tilde naught. So what does it mean? If we have E at the lambda t, where lambda is a diagonal matrix, this is equal to E at the lambda it, 1, n. So basically, we can say that after applying this transformation, every component of these new coordinates, x tilde, so x tilde of t is actually equal to a collection of terms in this way. Each one of these components will have an evolution that depends exclusively on the eigenvalue associated with that direction. So there's no mixing up with other directions. It's kind of a diagonal, how could I say, a decoupled solution, right? Because each state variable has an evolution that depends on its, the eigenvalue of its specific direction and the initial conditions on that specific direction. Now, what is interesting as well is that, so where I feel like what is the point we made here? You can make any transformation you want in the world to your x dot equals x plus bu, but there's a special one. If you take the special one, which is really related to the properties of A, then you get the simplest possible form of the x dot equals x plus bu. It's exactly the same as before, in the sense it has the same dynamics, the same system, same, let's say, solution. It's just a different way of writing it. But that's a simpler way of writing it. Why is it simpler? Because each x now can, the collection of n first order differential equations, each differential equation is solved on its own. It's decoupled from the others. Very nice, right? You don't have all those interactions as before. And there's another cool thing. Now, if you get the eigenvector, any eigenvector, and you set it as initial conditions for your system, you get an answer in time that is exactly that same shape, just evolving at the with a time constant that is dependent on the eigenvalue. So basically, if we have x of t equals e at the at x naught, but we choose x naught to be an initial condition, x naught to be one specific eigenvector, then the whole system, so all the possible state variables, will only evolve based on the direction given by that eigenvector at the frequency given by the eigenvalue associated with that direction. And this can be shown by, it's kind of the definition of so we have to leverage the definitions of matrix exponential eigenvalues and eigenvectors. I think that, depends on how much time we have. I think that I will, well, we can quickly do it. So the idea is that we're claiming this is the solution of the linear time invariant system. So what does this mean? If it's the solution of the linear time invariant system, it means it satisfies the equations of the linear time invariant system, which is x dot equals ax plus bu, but here we're just supposing that u is equal to 0, so we don't write it. Nothing changes if you put the u inside as well. So what's the solution to this? The solution to this, so x, we're claiming that so x is equal to e at the at x naught. If we put x naught equal to b, we get a at the at bi. So this represents the action of putting the eigenvector as initial conditions. Well, then x dot is the derivative of the left side is e a at the at times bi. Here we used the definition of matrix exponential. But this guy here, this can be written as, if we look at this here, if we take the derivative, it's x dot equal lambda I e at the lambda I t vi, and this is equal to e at the lambda I t lambda I bi, just to switch these two because these are scalars, so you can do whatever you want with them. And by definition of eigenvalues and eigenvectors, which is a bi is equal to lambda I bi, this term here is a bi, right? It's the same thing here. So if you see now we've got e at the lambda it a bi, and this term here is the same as this, and this means that this is a solution. We haven't really shown that this is the only solution, but we can leave it as an exercise. Linear time invariant systems have unique solutions. If this is a solution, there can't be another one. You can prove this later on. So what's the takeaway of this point? Takeaway here is that eigenvectors are special directions. It's so special that if you choose that to be the initial condition, the evolution of your system is only going to be that direction. There's nothing else is going to be involved. All other eigenvectors are going to stay on the side. So it's interesting. Why? Because now we can isolate the different components of the answer of the evolution of the whole x based on the individual eigenvector directions. It turns out that if your eigenvectors represent a base, that is, if they are linearly independent, which kind of happens if you have the distinct eigenvalues of the A matrix, then all the different, what's a base, mathematically speaking? A base is something that is, it's a collection of vectors that is, let's say, good enough to be able to represent any say in a vector space, any vector in a certain n-dimensional space. If we have the eigenvectors that are n eigenvectors because they're the same number as the dimension of the system and they are linearly independent, this means that anything that belongs to the world of our n can be represented as a weighted sum of these components, right? For example, any initial condition can be now broken down into components on the base represented by the eigenvectors. So basically what we're saying is that any initial condition can always be expressed as some combination, remember B is B1 to Bn, of some initial conditions that are in a different modal initial conditions, okay? So basically you can see that from x of t that was our e at the at x naught. Now we can, since each one of these components will excite only a dynamic on that specific direction, the whole evolution of the system can be expressed as a sum of shapes that evolve, each one of them only in a direction of a specific eigenvector, which is given by this Vi. And basically, the only thing that really changes is this x tilde 0. This initial condition, this modal, this weird thing that came out from this transformation. And this you can simply imagine it as a weight on each of the eigenvectors. Basically what we're saying is that if you take a system and you just choose any random initial condition, you can transform that initial condition in the favorite directions of the system. And after this transformation, what you're doing is as if you're poking the system on its favorite directions, favorite defined by if you poke it only there, it will respond only on that direction. You're poking it now in all these directions, but each one, you're giving different weights on how much you poke each one of these directions. And these weights are represented by these x tilde i's. So why is this relevant? It's relevant because now we showed that we can break down the evolution of a linear time invariant system in a bunch of directions that are related to the eigenvalues and eigenvectors of the A matrix. These combinations of eigenvalues and eigenvectors are called the modes of the system, and the x tildes are called the modal coordinates. So the eigenvectors represent the shape of each mode. The x tilde I represents some sort of weight on each mode at the initial conditions. And this allows us to basically justify the things we said before, that we assumed, hey, if you can make the system diagonal, then this is the answer. Well, you can make the system diagonal if you choose this a special coordinate transformation. And the conclusions, of course, are the same as we did before. You've got stability now if you have the eigenvalues that have a real part that is negative or equal to 0. Now, this is just a quick recap on, not really a recap, but I wanted to throw it in there because it's going to be useful as we move forward. How to express imaginary numbers. So there's always different I'm sure you know this, but let's just recap it. There's always different representations. You can have a Cartesian one and a polar one. If this is the real imaginary axis, an imaginary number has a real part and an imaginary one. You can put it here. The Cartesian form is just represented like this. The polar form has a phase, which actually we call the angle of z, and a magnitude. And different representations of these imaginary numbers are more appropriate for different situations. So we are introducing this because in the case of complex conjugate eigenvalues, you get these directions that are actually imaginary directions. So in order to play around with them, you need to be able to jump to between the different representations. And the Cartesian one is more useful when you want to sum up numbers. You want to sum up imaginary numbers because the math is simpler. You get to just sum up the real and the imaginary components separately. While the polar form is easier because when you multiply two imaginary numbers, for example, this one, and this one, say you take this here and you multiply it by something that is 1/2 E at pi half J. So basically, all you're saying is you're rotating it of 90 degrees and you are making the magnitude scale the magnitude of 1/2. So it's just a convenient way of playing around with numbers. So what's the point of the situation? The point of the situation is now we're able to describe evolutions of systems, and we know that these systems might have preferred directions, okay, that are related to the eigenvectors and the eigenvalues of the A matrix. That's what we refer to when we say the dynamics of a system, okay? What's the dynamics of the system? Well, we're saying how does it evolve? How does it evolve? It depends on the properties on which it evolves, and which fundamentally boils down to the eigenvalues. Now, the question is, through control systems, we want to affect the dynamics of systems, right? Because we want to make them behave as we want them to behave, as opposed to how they would want to behave naturally. So the question is, how can we affect this dynamics? If you remember, a few classes ago, I said, okay, there's two ways of doing like controls, right? That is two big, let's say, structures. One is, how do you get an airplane to fly, right? You just divide, no, what is it, the brick wall. How do you get the brick wall to fly? You just divide it by a brick wall, multiply it by an airplane. What does that mean? That was feed forward. Feed forward is, you want your output to be like a signal you desire. Well, as long as you know the dynamics of what you want to control, you know the representation, you know it's a brick wall, you can just multiply it by the inverse. You're canceling it out, and then you multiply by whatever you want it is to say. But that kind of is a mathematical solution that will never work in practice because we never have a perfect knowledge of the math of what's going on. The models are always wrong. They're always simplified descriptions of the physics, so this perfect cancellation doesn't work out. But then we introduced feedback, and feedback was this a little bit more magical idea of, let's not just send in a signal and choose the signal in a fancy way such that we get what we want as an output of the system, but let's measure the output of the system and literally do some operation with the reference signal. For example, check how distant, so a reference signal is where we want to be. Say this is the system we want to control. It has an input and it has an output. In feed forward, what we're doing is just saying, hey, put something here, a feed forward block, and see if you can operate some magic to get things to work. In feedback, we actually measure the output and feed it back, in the sense we actually go and do some operation of comparison with the reference signal that represents where I would like to be, where this represents where I actually am. And the difference, we can call it an error signal. And we feed directly the error signal now back to the plant with optionally some operation in the middle. That's what we call a controller. So this idea of linking back, closing the loop with a negative feedback actually has the very desirable effect to allow us to change the dynamics of the system. Actually change the eigenvalues of the A matrix, of course, of the equivalent A matrix that comes out from this closing the loop operation. So what I would like to do in the next 20 minutes is give you a teaser, an anticipation of what's to come. That is, show you a very simple example, a scalar case, in where we can do something that is extraordinarily powerful. That is, whatever you're given, whatever system you're trying to control, whatever its eigenvalue is, now we know that the eigenvalues tell us everything about the evolution of the system, we can arbitrarily cancel their eigenvalues and put other ones of our desire. So imagine that you're a control system engineer, you want to get a response of a system that has some specified properties. It doesn't oscillate, it goes fast enough, slow enough, whatever it is that you desire. And you can arbitrarily replace whatever your system is with whatever you want. That seems like the perfect way to go. This is a technique called pole placement. And today we're going to build up a little bit towards it to show you an example of how pole placement is powerful. And of course, we'll even see what are the challenges. In order to get there, we have to talk about two very important concepts. So remember how I started this lesson today with this thing that we're going to repeat over and over again, right? Which is, you got an input, you've got an output. In the middle, you've got a system. This system is regulated by this evolution of the state variables that you can imagine as a bunch of blocks, whatever, that are somewhat connected to each other and eventually link the input to the output, right? So we ask ourselves a question. Given a system, when we send in an input, can we affect all the state variables? That was question number one. And question number 2 is, just by looking at the output of a system, is it possible to understand, to discern, to distinguish the evolution of every single state variable that contributed to that output? Remember, the output y is equal to cx. It's a combination of the state variable, right? So the answer is not trivial in the sense that it depends. So we define these two concepts of controllability and observability. A system is said to be controllable if it's given any initial condition, initial state. It's possible to find a U, an input sequence, that takes the state and brings it to another place, okay? Nominally 0. It's the same if we were to say a different other state, a final state xf. Note that this does not say that it exists an input that takes the state to that final state and keeps it there. I'm just saying it brings, given any random initial condition, does it exist an input that allows us to pick the system and drive it to a combination of states where we want. If this is possible, the system is called controllable. If it's not possible, the system is called not controllable. This talks about how inputs affect the states. On the other side, this was question 1. Question 2 was how, so can we tell the states from the output? We define the concept of observability. Observability means if I get to measure, given any initial condition of the system, and suppose you're given a measurement of the output and the knowledge of the input. Is it possible to reconstruct what the initial conditions of the system were by just looking at the output and just looking at the input? It depends. Sometimes yes, or sometimes no. Imagine a very nonlinear system, but just to give you an idea, you're cooking and have a pan and you're making, I don't know, your sauce for pasta. I'm Italian, so I do lots of sauces for pasta. So you have your sofrito, you put some oil, you put some onions, whatever, garlic, your tomato sauce, your salt, your many ingredients. You have the input underneath, which is the fire under the pan. You get to choose how to regulate that. But you have a lid on the pan, okay? You don't get to see what's going on inside. Suppose the state variable, so the output of the system is the smell. I get to smell what's going on, okay? And I get to choose what the fire underneath it. And the state variables are whatever is going on that links the fire to the smell. All the very complex chemical relationships that go on between the ingredient, God knows what, right? So the problem is of observability. Suppose that it's the relative concentrations of water, salt, and oil, and then tomatoes inside of the sauce. So the question of observability is, if I change the observability, if I just smell the pan, is it possible to tell what all the concentrations of the ingredients are at any point in time? If I'm even told how I regulated the fire? I guess no, right? Unless you have a very simple sauce, no, it's a mess in this case, right? The question of controllability is, by just regulating the fire, can I drive the concentration of each single ingredient to wherever I want it to be? I'll put the fire to 0.707 turns so that the salt is going to be 3% with respect to, no, it's not possible, right? That's a system, it's not controllable, and it's not observable. So how do we write this in a little bit more of a general way? And for linear systems. The previous one was not a linear system. We can take intuition from the modal form. So to summarize really, what's the takeaway of the modal form? The takeaway of the modal form is that every system has properties that are structural, depend on what the system is, and are represented by the A matrix. That's fact 1. Fact 2, every system has favorite ways to respond to stimulus, favorite directions in the state space, okay? So combinations of x1, x2, x3. The special directions are called the eigenvectors, and if you change the coordinates in the modal form, that is, in the directions expressed by the eigenvectors of the A matrix, then you get a decoupled answer. Okay, that's nice, because if it's decoupled, it means you don't need to worry about what's the interactions between all the different x's. x1 depends on x01, x2 depends on x02. So, going back to the original system, if you put any random initial condition, your response can always be broken down to sums of the different modal coordinates. If we look at each one of the modal coordinates independently, you get that the evolution of one of the modal coordinates, one of the components of the x vector, is just given by the evolution of that modal coordinate and the input, of course, on that specific direction. So what's the thing that matters here? There's no influence of other directions. It's decoupled from every xj where j is different from I. And if this is true, then the output, which is cx tilde, it's just a combination of a linear combination of all the modal states, right? So let's see if we can keep this here while I show you. Whatever. So the idea, so we said, when is a system controllable? A system is controllable where there always is an input that can drive any state to wherever state I want. So intuitively, well, look at the modal coordinates. If each state is regulated by these equations, the evolution of a state is regulated by these equations, what happens here is that the input appears in those equations, so actually it is possible to have some effect with the input on that state variable, only if this bi tilde is different from 0. If this was equal to 0, you wouldn't have whatever input you plugged in, it would have no effect on that specific favorite direction of the system. On the other side, suppose that if the output is given by a linear combination of these terms, definitely if, for example, C2 here were to be equal to 0, this term, this direction x2 tilde, would not contribute to the output. So definitely there's no way in the world we would be able to reconstruct that part, that component of the initial condition by just looking at the output, because it wouldn't show up in its expression. So fundamentally, we can say that a system is controllable if, once you put it in modal form, every single bi tilde is different from 0. Remember that bi tildes are the components of b tilde, which, if I'm not mistaken, were t is equal to t inverse b, where b is the original b of the system, and t inverse is the inverse of t, which is the matrix composed by putting all the eigenvectors of A in columns, okay? And on the other side, a system is observable if and only if all the C tildes, the components of the C tilde, C1, C2, Cn, are different from 0. And this is why, because otherwise you wouldn't see that contribution of that specific state variable in the output. This is an intuitive understanding of controllability and observability. Now, suppose that not all your states are controlled. So where are we heading with this? Now, why do we care about controlling a system? Guess why? It's called control course. But the idea is, especially if we have a system that some of them, it has 100 state variables, 50 of them, 92 of them, 99 of them are naturally stable. They naturally decay in time and go to an easy place. But one of them, one of the modes of the system, is unstable. It tends to grow to infinity in time. Well, definitely we will be interested to design a controller such that we can grab that state that is going to infinity and change it, and change its dynamics and control it. So Controllability, as we defined it, means that every single state is controllable. We don't really require that. We require a system to be stabilizable. And then stabilizable is a word we use to define a system in which the subset of the modes that are controllable are only the ones that are unstable. Okay, we will continue next time.